If we're actually going to do anything useful in chemistry in a quantitative sense, we're going to need to understand about chemical equations, and most importantly, we're going to need to understand how to balance chemical equations. So in this video, we're going to start by reminding ourselves what chemical equations are, and then we'll finish off with some hints and tips about balancing chemical equations. Chemical equations are actually a shorthand notation for representing chemical reactions, and you can see an example of a chemical equation here. This represents the combustion of methane in the presence of oxygen to produce carbon dioxide and water. And this is a reaction that you might be familiar with because methane is the chief component of natural gas, and this is the reaction that takes place on gas stoves and in gas ovens. The chemical equation consists of substances. Here we've got a molecular compound, methane, we've got a molecular element, oxygen, another molecular compound, carbon dioxide, and a molecular compound, water. Each of the substances in a chemical reaction are given a subscript to represent the state of matter that they exist in at room temperature and pressure. So gas has the subscript G, liquid has the subscript L, and solid has the subscript S. The plus sign in a chemical reaction means reacts with, and the arrow means transforms to or produces. In this particular case, the arrow has a Greek capital delta on top of it, and that indicates that this particular reaction actually needs a little bit of heat to kickstart it. The substances on the left-hand side of the arrow are called the reactants, and the substances on the right-hand side are called the products. The big numbers in front of some of these substances are called the stoichiometric coefficients, and they are there to balance the equation. And this particular equation is balanced at the moment. And what the stoichiometric coefficient implies in the case of oxygen here is two lots of oxygen molecules. Each oxygen molecule has two atoms, so two lots of two. There are 4 oxygen atoms in total on that left-hand side there. Over on the right-hand side, the 2 in front of the water means 2 lots of water molecules. So you've got 2 times your 2 hydrogen atoms, and you've got 2 times the 1 oxygen atoms being represented there. We actually have a couple of invisible stoichiometric coefficients. The number 1 is never written in chemistry, and in a balanced equation, if a particular substance in the equation does not have an explicit stoichiometric coefficient, then a stoichiometric coefficient of 1 is implied. So we can represent chemical reactions using chemical equations such as this, where each of the substances are written as a chemical formula, or we can represent them using structural formulas. And structural formulas are good for us being able to readily identify the number of molecules involved and tracking exactly where those atoms are going. Remember, a chemical reaction is simply a rearrangement of atoms. So in this particular representation, we can see we've got 1 molecule of methane reacting with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water there. We can easily track where the atoms are going. We can see on the left-hand side we've got 1 carbon atom that's tied up in the methane molecule, and on the right hand side we've also got 1 carbon atom that's tied up in the carbon dioxide molecule. On the left hand side, the 4 hydrogen atoms are tied up in the methane molecule, whereas on the right hand side we've got 4 hydrogen atoms tied up in those 2 water molecules. 4 oxygen atoms on the left hand side are tied up in the 2 oxygen molecules, and we've got 4 oxygen atoms on the right hand side spread across the carbon dioxide molecule and those 2 water molecules. So this equation is said to be balanced. We've got equal numbers of atoms on both sides of the chemical equation there. The equation is a quantitative statement of amounts, and what that actually means is that exactly 1 molecule of methane will react with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. So if it's a quantitative statement of amounts, we actually know that the SI unit for amount is the mole. And so a different way of interpreting this chemical reaction or this chemical equation would be to say that 1 mole of methane molecules reacts with 2 moles of oxygen molecules to produce 1 mole of carbon dioxide and 2 moles of water. And this mole interpretation of chemical equations allows us to do some pretty useful things like calculating the amount of products from a given amount of reactants, or calculating the amount of reactants required for a given set of another amount of a particular reactant, for example. So in general, if we know both the reactants and the products of a chemical reaction, we can write an unbalanced chemical equation. And we simply balance that equation by placing the big numbers out the front, just by using those stoichiometric coefficients. A word of warning here, we should never change the subscripts in the chemical formula. By doing that, we actually change the identity of those compounds or elements. So the only way we can balance a chemical equation, once we've got the correct chemical formulas written, is to add those big numbers at the front, the stoichiometric coefficients. So we'll use the combustion of hydrocarbons as a particular example here. And a hydrocarbon is any compound that contains just carbon and hydrogen. The X and the Y here indicate that there's any number of ratios of carbon atoms to hydrogen atoms, representing hundreds or if not thousands of hydrocarbons that exist. Now, all hydrocarbons will combust in the presence of oxygen to produce carbon dioxide and water. So if we choose a particular hydrocarbon, propane, C3H8, we can write down an unbalanced equation for the combustion of propane. Propane, C3H8, reacts with oxygen to produce carbon dioxide and water. And at the moment, this equation is unbalanced, and we need to balance the equation by finding the appropriate stoichiometric coefficients at the front of each of these substances. It's unbalanced because we've got 3 carbon atoms on the left-hand side here, we've got 1 carbon atom on the right-hand side. We've got 8 hydrogen atoms on the left-hand side here and only 2 hydrogen atoms on the right-hand side. And at the moment, we've got 2 oxygen atoms on the left-hand side and a total of 3 oxygen atoms on the right-hand side there. So in order to balance this, we need to take a bit of a systematic approach, and here's some hints for balancing chemical equations. The first thing you should do is try and identify any elements in the equation, and we should leave them till last. So for example here, oxygen is an element. Remember, an element is a substance that contains the same type of atoms, and there's only oxygen atoms in this molecular oxygen here. So we're going to leave oxygen till last when we're balancing this equation. Identify atoms that appear more than once on either side of the equation, and we're going to leave them till later as well. So by that I don't mean there are 8 hydrogen atoms there and it's appearing more than once. What I mean is oxygen here is appearing in 2 substances on the right hand side. So that's a reason to leave oxygen till later as well. Identify hydrogen and oxygen atoms, and we're going to leave them till later in the process as well, particularly if water is in the chemical equation, because it's easy to balance hydrogen and oxygen atoms by adding some water molecules in that balancing process. And then all remaining elements we're then going to balance first. So in this particular case, that means we're going to be balancing the carbons first. We've got 3 carbons on this side and only 1 carbon on this side. So in order to balance the carbons out, I'm going to put a big 3 in front of the carbon dioxide. That gives me 3 times 1 carbon atoms on the right hand side, and that's good because it matches the 1 times 3 carbon atoms that we've got on the left hand side. The next element I'm going to try and balance is hydrogen. Remember, we're leaving oxygen till last. I've got 8 hydrogen atoms on the left hand side, and I've got 2 hydrogen atoms on the right hand side. So to balance those hydrogen atoms, I put a big 4 in front of the water. So that means my 4 times my 2 hydrogen atoms equals 8 hydrogen atoms, which balances the 1 times 8 hydrogen atoms on the left hand side. So what that's done now, it's given me a total of 10 oxygen atoms on the right hand side of this equation. The 10 oxygen atoms comes from the 3 times 2 oxygen atoms in the carbon dioxide, which is a total of 6, plus the 4 times 1 in these 4 water molecules, which is a total of 4 oxygen atoms, leaving me a total of 10 oxygen atoms in total on the right hand side. To get 10 oxygen atoms on the left hand side, I'm going to put a big 5 in front of the O2, and that gives me my 5 times 2 is 10 oxygen atoms to balance out the 10 oxygen atoms on the right hand side. So this equation is now balanced, and we've used a systematic approach to do it. We've got 3 carbon atoms on the left hand side, 3 carbon atoms on the right hand side. We've got 8 hydrogen atoms on the left hand side and 8 hydrogen atoms on the right hand side. And finally we've got 10 oxygen atoms on the left hand side and a total of 6 plus 4, which is 10 oxygen atoms on the left hand side there. In the next couple of videos to follow, we're going to look at more complex chemical equations to balance, and we're going to be looking at balancing chemical equations using polyatomic ions.